C is yeah, C is right. The electron accelerates more quickly, so it gets over to the proton a lot faster. Which arrow best represents the net force? We had one similar to this.
A, B, C, D, E.
Yeah, I used 1 through 5 as A3. Sorry, I think I changed all those. We used to not have clickers back when I first started here. We didn't have clickers. So we just used numbers on these little things. Can you imagine no clickers? You didn't have them either. At McNeese? Yeah.
They were a lot more complicated.
Yeah. 35, I'll stop. Or 38, let's say. B is right. Very good. Alright, so we did this before, but remind you, due to this charge on this force, we get a force that's in that direction and about that magnitude. And then due to this charge, we get a force that's twice the magnitude, because it's a charge that's twice as big. And so the net force will be in this direction. It was B that I marked, right? Mm-hmm. Yeah. Stop at 50. Just want to remind you too that if you feel like we're going too fast, that you can always like look at them ahead of time and just figure out what you think the answers are, and circle them in your book. And that way, when you come to this point, you can just put in the answer that you think is true. D is right. You'll likely see some of these relational type problems on the exam on Friday. E is KQ over R squared. And what am I doing? I'm doubling the distance and doubling the charge. So I double that distance and I double that charge. So that's 2 over 4. So I get 1/2 of the electric field, which was D. Which experiences the greater electric field due to the green charge? Red or the blue? All right, I'll stop at 58. All right, C is right. If you put B, you were probably thinking force. Which one experiences the larger force? But that's not, it's about the field. Which one experiences the field? And the field at this point right here, the +2 charge doesn't, it's not relevant for the field at that point. Like we can calculate that field as just KQ over R squared, where Q right here is this charge, the +1 charge. And so at this point and at this point, the fields are the same. Now they're going to experience different forces due to that field, but the field will still be the same. Which one experiences the greater force due to the green charge? I sort of did, yeah. I'll stop at 30 seconds. Just a few more seconds. D is the right answer. So you can think of Coulomb's law, or you can also think, F is equal to QE here. That's how we define what the electric field is. And so the particle with the larger charge feels the larger force in the same electric field.
Can you go back to that one,
This one?
the one, yeah, that one there. On that one, if you were gonna, like, say you had a practical or whatever, or free response, you wanted to work that out, would you make both of them equal to each other? Like, say, I guess what would be the formula you plug in, or is that just something you're supposed to know intuitively?
To find what?
To find out, you're saying E equals KQ R squared. So if we put numbers in there, I mean, how would you plug that in? Like if you knew the distance was, say, 3 meters.
Right. Well, yeah, so let's say that I had a 1 Coulomb charge here and a 2 Coulomb charge here. That's what you're asking?
Yeah.
And they're separated by, 1 meter or whatever. And if I wanted to find the electric field over here, right at that 2 Coulomb charge, I would say E is equal to K, which is 9 times 10 to the 9, times 1 Coulomb divided by 1 meter squared. Now what's not written there is an additional term that I'm just not writing because it's equal to 0, but that would be 9 times 10, no, it's not 0, never mind, I'm not going to write it at all. Can we rewind?
Sure, start off.
That's our electric field. This charge right here doesn't contribute anything to the electric field. Right here, because I'm at the point there, doesn't contribute to the electric field at that point.
That's what I was getting confused with, because I thought we were bringing them, I guess, together or whatever, finding the electric field in the center. Or something.
Right. Now, if you're looking, like more likely on the exam, you're going to have a point like up here and ask you for the electric field. In that case, there will be 2 vectors that you'll need to find the resultants of. Was it?
So, are you saying like if it would be like, you know how you have +1 and then +2?
Uh-huh.
That could mean that it wouldn't change a thing if it was +9 or anything like that. And
For the electric field at this location, right?
Yeah.
Now, everywhere else it's going to change the electric field, but at that location of the charge, it's not going to affect. All right? All right. Okay, we're almost done here. Uniform electric field in empty space, a 4 Coulomb charge is placed and it feels an electrical force of 12 newtons. If this charge is removed, 6 Coulomb charge is placed at a point, what force will it feel? Stop at 120. 120. 5 more seconds. Excellent. Right. This is just a simple calculation. You first have to find the electric field. I know that F equals QE. And for a 12 newtons on a 4 coulomb charge, the electric field must be 3 newtons per coulomb. And then, if I put in a 6 coulomb charge at 3 newtons per coulomb, then that gives me the 18 newtons. Remember, this is our definition of the electric field. That's how we define the electric field. All right. I'm going to go ahead and sort of. We haven't done field lines yet, but let me go ahead and. Well, we'll come back to this. We'll come back before the end of class. By the way, I'm expecting the exam next week on Friday to cover all of Chapter 1, obviously, and a portion of Chapter 2. We are definitely not going to get up to capacitance for Chapter 2. Chapter 2 is a pretty big chapter. We might not get up to electric fields and potentials where you have to do the partial derivative. You haven't done partial derivatives before, have you? You have done them? Okay, we might not get into that. That might be on the exam. But we will definitely do electric potential and potential energy.
Do you guys still have that thing on the website or anything? Which questions?
No, that was all for last semester. But I will make something like that for y'all. Is that good? All right. So anyway, we'll deal more with that next week. I'll give y'all a better idea. All right, so let's look at electric field lines. If you're in the lab, I think most of you are in the lab, right? How's that going, by the way? Yeah. All right, good. Huh? The computer lab?
Yeah.
Yeah, it's fun, huh? Do you like the little computer games and stuff? Yeah, I like it.
Hockey what?
Electric field hockey.
It helped make sense to you, once you saw how it worked, it kind of brought it all together.
Right. Yeah, I like that lab. It's fun. All right. There are some links here. I'll send them out to the class about Michael Faraday, and you can watch those on your own time. But there's a whole PBS special about Einstein. I think it's called Einstein's Universe, and you can download the whole thing on YouTube. But it has a nice introduction to Michael Faraday. It's just sort of for historical purposes. We're not going to watch it either. But I'll send the link out for you. It's kind of interesting to watch, sort of about how electricity came about and the study of electricity. We might watch it later when we get into magnetism because it's more relevant there. But Michael Faraday developed the idea of electric field lines, and these are just a tool to define or to describe electric fields. And they're used to describe other fields too, like gravitational fields. There are a couple of rules about electric field lines. First of all, the electric field is tangent to the field lines. I'll show you what I mean by that in just a second. The electric field is tangent to the lines. And the magnitude of the electric field is denoted by the density of the field lines. And here's the link. This is what y'all did in lab, the PhET simulation. So if you want to play with that some more, you can do that. Can I go down from here? I'll show you what I mean by these rules.
Hold on a second.
Okay. Did anybody use the word equidistant the other day? No?
I thought about it. I got the shot.
I think it would be really nice to use it at, like at McDonald's when you're ordering something.
So I in the lab, she used.
Equidistant?
Yeah.
Yeah, I'm not sure how you could use it at McDonald's, but I think that,
How much equals equidistance from each side?
yeah, then you would just be weird. You ever heard of it?
Actually, I was going to say the same example.
The pickles. I was thinking the same example, actually. The pickles should be equidistant. Or they should form an equilateral triangle on my cheeseburger. Yes, yeah.
See how destroyed your brain comes out.
Okay. Oh, this is a third rule here that you know. We'll call this the third rule. That field lines emanate outward for a positive charge and inward for a negative charge. Remember how we defined the electric field? The electric field is the force that a positive test charge would feel if it were in that position. So if I imagine a positive test charge here, this is that you pull out of your back pocket, right? Your positive test charge, and you place it above that positive charge, then the field line, or the force rather, is going to be in that direction. And so the field line will be in the same direction. So for a positive particle, this plus Q charge, the field lines always emanate outward. For a negative charge, these are two separate situations here. For a negative charge, if I have a positive charge here, it's going to feel a force in that direction, and so the field line will go inward. So they always originate at a positive charge, and they go into a negative charge. Now for rule 2, which had to do with the density of the lines, here I have a charge with 2 points A and B, and at point A, the field lines are more dense than at point B. That just means they're closer together. So here the field lines are this close together, here the field lines are this close together. So the electric field at point A is larger than at point B. And you can think about that too, like if I have a positive particle here, it's going to feel a really big force, whereas if I have a positive particle out here, it's going to feel a markedly smaller force because of that 1 over r squared dependence. All right? Andrew?
Would they both end up at the same distance away from the positive molecule?
Why would they end up at the same distance?
Well, I'm asking because if each charge is going to be like 1 coulomb at A and B, people at A would, I guess, accelerate faster, but would they end up at the same distance away?
They would feel not at the same time because particle A is going to accelerate more quickly at the beginning. Like if you just
more distance to travel though, because it's closer to the charge.
no, they won't end up at the same place. Not at the same time. I can't explain that quickly, but like if you looked at the kinematics of it.
Same distance away though, like.
I understand what you're saying. Right, I understand what you're saying. You're saying that particle B starts out slower, accelerating more slowly than particle A, but since particle A has a longer distance to go, then maybe, like let's say that we have this finish line out here. Would they reach that finish line at the same point? Is that what you're asking? No. It's it's a little bit more complicated than we've done because the acceleration is not constant. As they move outward, the acceleration decreases, which we've never really dealt with. So you'd have to use calculus to solve that, or a differential equation to solve that. All right, that's a good question though. Recognize project. Yeah, Jose?
For question number 3 in the negative side, does it really have to be? What if it's just a charge that's on the electric field? There's none on the opposite charge there.
Right. So it doesn't have to. Your field lines don't have to end at a negative charge. We'll see some examples of that.
No. What I'm saying is like, what if? Let's assume the electric field is empty, right? There's nothing in it.
Okay.
We put a negative charge there. Then would that rule still apply that everything goes through?
We'll get to it in just a second. I'm going to show you some. Y'all did this in lab, but I'll show you some more.
Yeah, that's what I was asking because I saw it in the lab thing where you put one and then you put the other, but when I put the negative on its own, all the arrows were still going to the negative one, even though it was not positive.
Right.
If you get what I'm saying.
I think I do.
Okay.
Yeah. We'll get to 2 charges in just a second. All right. So I've already said this, but the force a positive test charge feels is larger than it feels in part B. All right, let's look at a little bit more at field lines. Some more rules. Goodness. Oh yeah. So the lines for groups of charges. It's like in our house, we say there's always more rules. Like this is rule number 139. You must not hit your sister. No, we try to have no rules, and then they can't do anything wrong, right? Like if there are no rules, people do nothing wrong. The lines for groups of charges. Must begin on a positive charge and end on a negative charge. Or I'm not going to say begin on a, not must, begin on a positive charge and end on a negative charge. If there's an excess of charge, the line will end at infinity. Let us say it won't end. And then number 2, which I'll write in blue, the number of lines on a charge is proportional to the magnitude of the charge. Proportional to the number of lines on a charge is proportional to the magnitude of the charge. So a charge 2Q will have twice as many lines as a charge Q. I'll show you a picture in just a second. And then, I don't know why I write this, but I think it's because of Ghostbusters. Like I really like Ghostbusters when I was a kid. Field lines never what? Never cross. Don't cross the streams. Maybe Rob and I were the only ones that got it. Okay, so field lines never cross. Alright, so for example here, I have field lines that start at the plus Q and go to the negative Q. And they're going to distort a bit. Remember, the electric field is tangent to these lines. So like, for example, here, my electric field, my net electric field is in this direction. It's tangent to the line. And if I think about that, I have 2 field vectors. I have one vector that's here, and then another vector that's here. And when I add those 2 vectors up, I get an electric field that's in that direction. I get 2 vectors because I have 2 charges that are generating an electric field there. Electric field lines come here as well, and they're all, since I have 2 equal charges, they're gonna have all the lines that start in the plus Q charge are gonna end in the negative Q charge. We know when I can go on.
So if you, in the opposite direction of the electric field, if it has to for, like, say, the negative direction of electric field, you would always have it going away from the positive charge.
Right. And towards the field lines always start at positive, end at negative. All right. May I go on?
I was just trying to figure out what you did in that top corner.
It's okay. May I?
You can go.
All right. All right. So if you have an excess of charge, I get some field lines that come here, like this. But then when I have extra field lines, That look like that. So notice that I have 3 field lines that go into this charge. So how many should I have coming out of the plus 3q charge? If the number of lines that come out of the charge are proportional to the magnitude of the charge, how many field lines should I have coming out of the 3q charge? I should have 9, right? 3 times as many field lines. And so now notice now that I have 9 field lines coming out of that charge. That was that rule number 2? Yeah, so that was rule number 2. So plus 3q charge has 3 times its number of field lines. As the minus q charge. And here, if I have 2 positive charges, I can have, your field lines are going to look like this. If you're in lab, you've done this. I would draw it with 2 field lines coming out like that, and then I would draw 6 field lines to denote the greater magnitude of the field. Oop, that's wrong direction. Like that. These are just a tool. It's just something to help you to imagine what the field looks like. So, I mean, in reality, there are an infinite number of field lines. Well, not an infinite number.
Can we have stuff on the test where we draw the field lines?
You could, yeah. There's some homework questions but they would not be terribly complicated. I mean, it would be like point sources like this. Are all of you in lab? Who's not in lab? Anybody? Yeah, it would just be point sources then. We wouldn't do regular objects. Though in lab, you did do something else that we'll deal with in a couple of chapters, and that is 2 charged plates, where I have plus and minus charged plates. And in that case, you have field lines that look like this. And we'll find that's the case for a capacitor. And we'll also use that idea to develop the idea for voltages potential.
On the plus 3 charge, you have 6 lines coming out of it. Is there a reason you picked 6?
Yeah, because I had 2 lines. I drew 2 over here. I needed 3 times as many.
3 on the plus q.
So that'd do 9. Yeah.
So it's proportional to
The magnitude of the charge. Yeah, that's the point.
So you just drew 2
Just because. I mean, I could have drawn 1 and 3, 2 and 6, 3 and 9.
That's what I was trying to say.
Whatever. Right. All right, let's try this quick test, then we'll finish up that concept test. If you don't like this material, hang on, we'll be at circuits soon. Circuits are a lot more fun than this stuff. I think most people like circuits. Circuits are like puzzles. They're like Sudoku, kind of. Circuits are like Sudoku, yes.
Did you know that,
Everything's like Sudoku to me. I like Sudoku.
Did you know that the for Sudoku puzzle to be only have one solution, it needs 16 beginning letter numbers.
No, I didn't know that.
It needs 16, or it'll have multiple solutions.
Oh, that's interesting. Alright, I'll stop at, let's do about 10 more seconds. 1:15. That must be right, let me see. Alright, so the left charge has a magnitude of 6 microcoulombs, and because the field lines are going into it, we know it must be minus 6 microcoulombs. And then the right charge has twice as many field lines. It has 12 field lines, whereas I only have 6 field lines over here. So we know it has to be twice the magnitude and positive, which is plus 12. I think that's the end. Let's finish up this concept test and we'll be done. Got my might even get out momentarily. Where is it? Here we go. What are the signs of these charges? Green and the red. If you can't see it, the arrows are pointing in this direction. From the right to the left. Stop it. Yeah, Joseph. Okay, we only have one or two more questions. It shouldn't. Okay, I wouldn't sweat it. All right, I'll stop at 35. He is right. Negative because they end there, positive because they originate there. This last one. Which of the charges has the greater magnitude? The green or the red? Are both the same. I'll stop at 20. All right, so don't forget that the test is on Friday. If you want to move on ahead, you know, if you go to the 101 site, much of what we'll be doing in the first part of Chapter 2 we're also doing similarly in Physics 101, and there's a screencast there for the first part of that chapter. So if you want to look at that, that's fine. A lot of it's going to be the same until we get to the partial derivatives. I can send that link out to you. And we need to do one of those derivations. I'll send this out in an email to you, but you need to do one of those derivations for the test on Friday. You can use whatever resources you want. I'm pretty sure they're on the internet, but if you can't find them, you can come see me. I'll give you a textbook you can look at. Or if you don't have access to it or whatever. All right? Have a great day. Have a good weekend. Careful.